Dear students, in this video on magnetic effects of current, we will study torque on a current carrying loop placed in magnetic field, moving coil galvanometer, its conversion to ammeter and voltmeter, and numerical problems based on these topics. So let us begin with the first topic, which is torque experienced by a current loop placed in uniform magnetic field. So we have chosen a rectangular loop PQRS of sides B and L, length and breadth. It is placed in uniform magnetic field B at an angle theta, and current I is passing through this loop, right? Now, if you look at this now, see, this loop consists of 4 conductors PS, PQ, QR, RS, and each conductor can be treated as a current carrying conductor placed in uniform magnetic field. So we can find out force on this one, force on this one, force on this one, and force of this one, and then we can find out their combined effect. Okay, so we'll find out the force on side SP first. Let's look at this one. If you look at this one, let me begin with force acting on this side SP. So here this is the magnetic field B, right, and this is the current element. You know that the length element is along the direction of the current. So when you take this cross product B cross B and you use your right hand screw rule, then the force will be directed upwards. So force acting on this side is upwards. It is perpendicular to the side PS and it is upwards, right? And its magnitude is, see, F1 is I B cross B. You have done this relation that F is equal to I L cross B. So here the length is B, vector B. So the magnitude of this force is I B B sine theta. You know cross product is AB sine theta, and direction is upwards along the according to the right hand screw rule. And now force on side QR. Now look at this side QR, which is the opposite side, and now the direction of vector B is this one, direction of magnetic field B is this one, and when you take their cross product B cross B, then that will be directed downwards. Now using your right hand screw rule only. And then look at the relation now. See, the force F2 is downwards and the relation is F2 is I B cross B, or F2 is I B B sine theta acting downwards, and you can see that F1 and F2 are equal and opposite forces and they are acting along the same line of action. So that means they are cancelling out each other. They are not contributing to any kind of motion. So F1 is equal to minus F2. They do not produce motion, right? Now we'll try to find out force on this side and on this side, the remaining two sides. So let us have a look at them now. See, the magnetic field at this point is along this direction, you can see, and here what you can see is the angle between this magnetic field and the length is 90 degree. The angle between L and B is 90 degree, right? So L and B are perpendicular to each other and direction of vector L is this one. See, direction of length vector is along the direction of the current. So at this point, the vector B is along this direction and vector L is along this direction. And when you find out L cross B, see L cross B, using your right hand screw rule or Fleming's left hand rule. So what you get is F2 is equal to, this is going to be F3. It will be directed outwards, and on the opposite side here, the force will be directed inwards, and see F4, and F3 and F4 will also have same magnitude. See, the distance between this force and this force is B sideways. It is equal to this B only. And if we try to produce it backwards, then the perpendicular distance between these two forces is this one, as you can see, right? I can choose another color here. See, if I try to produce it backwards, then the force between them is, the distance between the two forces is this one. So you can see that F3 and F4 have different line of action. So they will not cancel out each other. Rather, they will produce a torque. So relation for force acting on side PQ, that is P3 is equal to IL cross B, and here ILB sine theta, and the angle is 90 degree. So it is just ILB. Force on side RS is IL cross B again, and its magnitude is ILB sine theta, and theta is 90 degree. So the magnitude is ILB and ILB in both the cases, right? Now F3 and F4 are also equal and opposite only, but they have different line of action. See, they are equal and opposite here. I can show you. F3 and F4 are equal and opposite. They have same magnitude, directions are opposite, but they have different line of action. See, the forces are parallel, acting along different lines, so they make a couple, right? And I want to show this couple once again. So see, if I try to produce this line backwards and drop a perpendicular from here, then you know that torque or moment of force is either of the forces multiplied by the distance between them. So I know this force as ILB, and we will find out this distance, the perpendicular distance between this line of action, their line of actions. So using all the given information, like this side B, the angle between magnetic field and the plane of the coil, we will find out the torque acting on it. So the net force acting on this whole system is 0. Important point to note. F1 is cancelling out F2. F3 and F4 are equal and opposite. So net force on the system is 0. But this F3 and F4 produce a torque, make a couple, right? And that means they will try to turn the coil. वो coil को turn करने की या मोड़ने की कोशिश करेंगे. So let us try to find out this torque. So we have these two forces, F3 and F4, and the separation between them is B, the side is B, and the magnetic field B at an angle theta, right? Same as in the previous picture. And now I have produced this side, this force F3 in backward direction, and now we have dropped a perpendicular distance between these two forces, and if you look at this, the angle between this side B and magnetic field B is theta, and if you drop this perpendicular, then you will get this alternate angle as theta. Now this side is B और एंगल के साथ वाला कॉम्पोनेंट हमेशा ही cos होता है. So B cos theta. So B cos theta is perpendicular distance between the force F3 and F4. So these two things are required by us. Now we need to define one more vector here. This vector is normal to the plane of the coil, as I have shown you here. So, and the vector is area vector, and you are familiar with area vector. See, it has magnitude equal to area of the loop, and it is acting along the normal to the loop. तो एरिया वेक्टर उस लूप के एरिया के परपेंडिकुलर या नॉर्मल होगा, right? And we will define another vector M. I'll discuss that later. And this angle is phi, and let us discuss the calculation part. So torque is equal to force into perpendicular distance between them, which is B cos theta, and F3 and F4 have same magnitude as ILB, right? So putting the value of F here, we get the torque as ILB B cos theta. Now bring this L length and breadth together, you get area. So IAB cos theta, right? And now the next step is here. If the coil has n turns, then the torque will also become n times. So you get NIAB cos. Now let me talk about this angle. Now this angle theta is known to you, and the area vector is along the normal, and this angle is phi. So that means theta plus phi is equal to 90 degree, or theta is equal to 90 minus phi. So I have placed 90 minus phi, and cos 90 minus phi is sin phi, right? And NIA is taken as M. So it becomes MB sin phi. And now let's see what is M. So where phi is angle between normal to the coil and the direction of the magnetic field, right? And we are going to discuss this M. See, M is equal to NIA. M is equal to NIA. It is called magnetic dipole moment of the coil, and it is a vector quantity. Look at it. This is M is a vector quantity along the area vector, and its magnitude is given by NIA, and its SI unit will be equal to करंट की यूनिट है एम्पियर और आपका एरिया है मीटर स्क्वायर. SI unit is this one, and it is directed along the, if you have a magnet, I have already discussed this, if you have a magnet with a south pole and here north pole, then it is directed from south pole to north pole. But here I have a loop, so if the magnetic field lines are outwards, that means the current is anti-clockwise, then the direction of M is this one. And if the magnetic field lines are inwards to the coil, then see, in this situation also, the direction of dipole is, magnetic dipole is this one. Okay. You will require these things while doing your numerical problems. So it is called magnetic dipole moment of the loop. Now, let us get back to this once again. So this torque is equal to MB sin phi, and M and B both are vectors. So I can write the vector form of this torque. Torque is a vector, M and B both are vectors. So torque is equal to M cross B, right? And you know that magnitude of M cross B is AB sin theta. And let us see special cases. When this phi is a right angle, when this angle is a right angle, that means say the magnetic field is along this direction. ठीक है? So plane of the coil is parallel to magnetic field, then the torque experienced by the loop is maximum. That means if the plane of the coil and magnetic field are along the same direction, then the area vector and magnetic field will be perpendicular and torque experienced by it will be maximum. It will be equal to MB or NIAB. Right? And now, when this phi is 0 degree or 180 degree, that means the plane of the coil is perpendicular to magnetic field. Let's look at this one. Phi is 0 means the magnetic field is along this direction. That means the area vector and magnetic field are along the same direction, or magnetic moment, magnetic field, area vector are along the same direction. That means the plane of the loop is perpendicular to magnetic field. In all such cases, the torque will be 0 because this sin phi is 0. See, torque is equal to mb sin phi. Sin phi 0 हो गया, 0 और 180 डिग्री के लिए, तो torque यहाँ पर 0 हो जाएगा. So these situations should be very clear to you. So let us move on to moving coil galvanometer, which is direct application of the previous derivation. So it consists of two cylindrical poles, north pole and south pole, which establishes a magnetic field between them. And then we have a coil, magnetic coil suspended between these poles with the help of a wire. And this wire is a very special wire. It is called phosphor bronze wire. And then it is attached to a hairspring and connected to this terminal. Right? And now a mirror here, and see, this is one end of coil, this is the other end of the coil, and the ends of coil are connected to this battery or cell, and in this way the circuit is completed. The coil is connected to a source of current, and when this key is closed, the current starts flowing. See, key is closed, current starts flowing in this coil. Right? See, the current is flowing in the coil, and when the current is flowing in the coil, it will experience a torque. See, a current loop placed in magnetic field experiences torque. So as soon as this experiences torque, coil will take a turn, और coil turn होगा तो ये जो वायर है, ये जो phosphor bronze वायर है, ये ट्विस्ट हो जाएगी, मुड़ जाएगी. और जब कोई भी चीज़ को आप ट्विस्ट करके छोड़ते हैं तो वो वापस खुलने की कोशिश करती है. सो ये जो वायर जो ट्विस्ट हो चुकी है, ये वापस खुलने की कोशिश करेगी. राइट? सो इस कॉयल में होगा डिफ्लेक्टिंग टॉर्क और इस वायर में होगा रेस्टोरिंग टॉर्क. और जिस पोजीशन पर इसका डिफ्लेक्टिंग टॉर्क और इसका रेस्टोरिंग टॉर्क इक्वल हो जाएंगे, वहाँ जाके कॉयल रुक जाएगी. So that becomes its equilibrium position. And one more thing, ये जो आपको ग्रे कलर का दिख रहा है, this is soft iron core. This is soft iron core. So coil को इस soft iron core के ऊपर लपेटा हुआ है. And we will see the purpose of all these things later. So starting with principle. A current carrying coil placed in magnetic field experiences torque. This is the principle, and the different components you can see: a mirror, cylindrical poles, rectangular copper coil. This coil is made up of copper, and then it is wound over a soft iron core here and suspended with the help of phosphor bronze wire. So the structure and all is clear, and working I have explained, but we'll see it once again. When the current passes through the coil PQRS, it experiences deflecting torque due to magnetic field. Now, due to this, the deflection of coil, the phosphor bronze wire gets twisted. So, a restoring torque sets in the wire, and in equilibrium position, the deflecting torque becomes equal to restoring torque. You can see the working. So, we will find out the deflecting torque and we will find out the restoring torque. Okay. So, now deflecting torque is NIAB sine phi, where phi is angle between this area vector and magnetic field, and this is equal to K theta, where theta is deflection in the coil. So, this phi and theta are two different things. Now, this K is equal to restoring torque per unit twist in wire, per unit angle of twist in wire. Okay. Now, to make the scale linear, linear means direct relationship, torque must be constant. So, the angle phi between the magnetic field and area vector is made right angle by using radial field. So, I'll just tell you about radial field, but before that, just look at this term, sine phi. If somehow this phi is made 90 degree, the value of sine phi will become 1 and the torque will become NIAB, constant. And a right side is constant, K theta, right? So, it will make the scale linear. How it becomes? Let us look at the next page then. Okay, here. So, phi is 90 degree, torque is equal to NIAB is equal to K theta, and okay, I just change the side here. You get current I is equal to K upon NAB theta, right? And if you look at the terms inside the bracket, this is constant, right? So, from here I can show that I is equal to G theta, the constant is G, galvanometer constant, or the current becomes directly proportional to theta. That means jitna zyada current utna zyada deflection. When current is doubled, deflection is doubled. This is called linear scale. Okay, and this is why we required to make this angle phi as 90 degree. And for this we use radial field. So, what is radial field? We'll just find out the value of G here. Let us look at this radial field. See, for this radial field we use cylindrical magnetic poles, right? So, the magnetic field will start from North Pole, and this is the top view of the galvanometer. So, this grey part is soft iron core, and the property of soft iron core is it attracts magnetic field lines. So, what happens? Magnetic field lines start at North Pole and they are attracted by this soft iron core. So, it enters inside it and then they are attracted by South Pole. So, in this way you get magnetic field lines like this one. So, what happens when this you can see these lines as the cross section of the loop, the top view of the loop. So, loop किसी भी पोजीशन में रहे, loop ऐसे रहेगा तब भी वह मैग्नेटिक फील्ड के पैरेलल है, लूप ऐसे हो जाएगा तब भी मैग्नेटिक फील्ड लाइन के पैरेलल है. लूप को हम कैसे भी रखें, किसी भी सिचुएशन में आप रख दीजिए. इफ लूप इज प्लेस्ड लाइक दिस, वो इन मैग्नेटिक फील्ड लाइंस के पैरेलल है. इफ इट इज प्लेस्ड लाइक दिस, ये इनके पैरेलल हो जाएगा. ऐसे रख दिया हमने लूप को तो पैरेलल हो जाएगा. दैट मीन्स इन एवरी केस द plane of loop and magnetic field are parallel, or plane of loop and the area vector are perpendicular. So we have made the angle between area vector and magnetic field perpendicular to each other by using this radial field and by using the soft iron core. So this is exactly same what I just told you. The plane of coil PQRS lies along the magnetic field lines of force, and in whichever position the coil comes to rest in equilibrium. So the angle between plane of coil and the magnetic field is 0, or the angle between area vector, which is normal to the plane of coil, and the magnetic field is 90 degree. And I had shown you one mirror also. So let us look at the role of the mirror. See, when the coil gets deflected, suspended by this wire. Now this wire is phosphor bronze wire. So when the wire twists, the coil turns, this mirror also turns, and here we have a lamp. So light of lamp falls on it, it gives deflection. When it takes turn, it deflects through some angle which can be easily measured. Okay. Now look at this part. Radial field is produced by using cylindrical magnetic poles and soft iron core. आपके एग्जामिनेशन में क्वेश्चन पूछा जाता है कि हाउ इज रेडियल फील्ड प्रोड्यूस्ड एंड व्हाट इज द रोल ऑफ अ रेडियल फील्ड. ओके, तो ये ज़रूरी नहीं है कि पूरा का पूरा आपको एक साथ पूछें, वो बिट्स एंड पीसेस में भी क्वेश्चन पूछते हैं. सो लेट अस लुक एट दिस अनदर टॉपिक, current sensitivity of a galvanometer. Now first you must understand the idea of current sensitivity. See, a galvanometer is used to detect current. So वो वाला galvanometer जो छोटी से छोटी करंट के लिए ज़्यादा डिफ्लेक्शन देगा. A galvanometer which gives large deflection for small currents will be said to be more current sensitivity. So how do we measure this current sensitivity? It is the deflection in galvanometer when unit current passes through it. So it is deflection per unit current. See? So current sensitivity SI is theta upon I, and theta upon I is equal to NAB upon K. So to increase the current sensitivity, we must increase NAB, number of turns, area of the coil and magnetic field, and this K should be small. Now K is restoring torque per unit twist of the phosphor bronze wire. जिस वायर से हमने इसको लटका रखा है, इसका ये restoring torque per unit twist है. इसका मतलब ये है कि छोटे से छोटे टर्न के लिए भी there will be large deflection. So that is why we use phosphor bronze wire, because it has small value of K. So आपको ये भी पूछ सकते हैं कि what is the role of a phosphor bronze wire? Why do we use phosphor bronze wire? So you should know that it has very small value of K. Now voltage sensitivity. It is the deflection in galvanometer when unit potential difference is set up across its terminals. That is deflection per unit potential difference, and you know that V is equal to IR, where R is resistance of the loop or the coil. So putting the values, you get NAB upon KR, और इसको बढ़ाने के लिए again N, A and B should be large, K should be small, R should be small. Okay. And now conversion of galvanometer into emitter. Now see, emitter is used to measure current, you know that, and role of galvanometer is to detect current in a circuit and also detect its direction. सो गैल्वेनोमीटर बहुत ही कम करंट को डिटेक्ट करने के लिए बनाए जाते हैं, तो गैल्वेनोमीटर में से बहुत कम करंट पास होनी चाहिए. नाउ I want to make it suitable for measuring large currents. So what happens? If I is the current, then we connect a small, very small resistant in its parallel. This is called shunt. It is like providing a bypass to a current, no? So गैल्वेनोमीटर में छोटी सी करंट IG चली जाएगी एंड रिमेनिंग करंट I माइनस IG वो शंट से पास होगा, ठीक है? और सर्किट में करंट है I. See, if I try to complete the circuit, see, I can have a resistance here, a cell here, and in this way सेल से करंट रेसिस्टेंस में आई और यहाँ पर आ गई और इधर आ गई, और गैल्वेनोमीटर में छोटी सी करंट चली गई IG, और रिमेनिंग करंट के लिए हमने बाईपास दे दिया एज अ वेरी स्मॉल रेसिस्टेंस. दिस इज कॉल्ड शंट, ठीक है? सो दिस होल, ये वाला जो अरेंजमेंट बना, दिस अरेंजमेंट इज कॉल्ड एमिटर, और ये वाला अरेंजमेंट इस आई करंट को नाप पाएगा बाय सुटेबल कैलिब्रेशन, राइट? सो galvanometer can be converted into emitter by connecting a very small resistance in its parallel called shunt. अब इसकी मुझे शंट की वैल्यू कैलकुलेट करनी है. So if you look at it, the potential difference from here to here across this shunt and across the galvanometer is equal. They are same. See the potential difference equal, or potential difference across the galvanometer is Ig into G, where G is resistance of the galvanometer. So potential difference is Ig into G, and across this one the current is I minus Ig into resistance S, and the value of the shunt now is this one. S is equal to, just change the side, this S is equal to Ig upon I minus Ig into G, and resistance of emitter. अब ये जो combined emitter हमारा बन गया, ये just look at this one. This whole is an emitter. तो यहाँ पर देखो कि G और S पैरेलल में है, तो resistance of emitter is GS upon G plus S, पैरेलल में है, and resistance of an ideal emitter is 0. आइडियल एमिटर का रेसिस्टेंस 0 होना चाहिए. दैट मीन्स कि जब कोई करंट इससे पास हो रही है तो इसके अक्रॉस पोटेंशियल डिफरेंस 0 होना चाहिए, बट दैट डज नॉट हैपन. दीज फॉर्मूले आर इम्पॉर्टेंट एंड द वर्किंग इज ऑल्सो इम्पॉर्टेंट. सो कन्वर्जन ऑफ गैल्वेनोमीटर इनटू वोल्टमीटर. नाउ हियर what we do is we connect a high resistance in series with a galvanometer, और सर्किट हमारा कुछ भी है, it can be a resistance here, a cell here connected like this, and current is moving like this. Now in the galvanometer only IG current will pass, very small current, जिसके लिए galvanometer पूरा का पूरा डिफ्लेक्शन देगा, और बाकी सारी करंट इस रेसिस्टेंस में से पास हो जाएगी जिसके अक्रॉस मुझे वो पोटेंशियल डिफरेंस नापना है. सो दिस सीरीज कॉम्बिनेशन गिव्स a voltmeter, and you know that voltmeter is connected in parallel. So हमारा एम है इस रेसिस्टेंस का के अक्रॉस यहाँ से यहाँ तक पोटेंशियल डिफरेंस निकालना. So high resistance is connected in parallel with the galvanometer, right? So galvanometer can be converted into voltmeter by connecting a very high resistance in series with it. Now we are going to find out its value. So potential difference across the given, this is the load. The potential difference across the given load resistance is sum of potential difference across galvanometer and potential difference across high resistance. So इसका और इसका टोटल पोटेंशियल डिफरेंस सीरीज में है, दोनों रेसिस्टेंसेज ऐड हो जाएंगे. सो द टोटल पोटेंशियल डिफरेंस इज IG into G plus R, और मुझे तो इस सीरीज रेसिस्टेंस की वैल्यू निकालनी है. सो जस्ट चेंज द साइड. ये आई जी ने यहाँ आके डिवाइड कर दिया वी अपॉन आई जी एंड माइनस जी. ओके. एंड रेसिस्टेंस ऑफ द वोल्ट मीटर सीरीज में है जी प्लस आर. सी. एंड रेसिस्टेंस ऑफ एन आइडियल वोल्ट मीटर शुड बी इनफाइनाइट. वोल्ट मीटर का रेसिस्टेंस इतना ज़्यादा होना चाहिए कि इससे मेन करंट से बिल्कुल भी करंट ना ले, नहीं तो मेजर्ड वोल्टेज एक्चुअल वोल्टेज पोटेंशियल डिफरेंस से कम होगा. एंड लेट अस मूव ऑन टू न्यूमेरिकल्स नाउ. दिस इज NCERT numerical, unsolved numerical. As you can see, 4.27. A galvanometer coil has a resistance of 12 ohm and the meter shows full deflection for current of 3 milliampere. How will you convert the meter into voltmeter of range 0 to 18 volt? So that means हमारा ये जो वोल्ट मीटर है उसकी रेंज 18 वोल्ट तक की होगी और गैल्वेनोमीटर की जो करंट है मैक्सिमम पॉसिबल करंट दैट कैन पास थ्रू गैल्वेनोमीटर इज 3 मिली एम्पियर. So let's see how we solve it. We know that R is equal to V upon Ig into G. R must be connected in series with the galvanometer. And putting the values here, the value of V is 18 volt, range of voltmeter. The current Ig is 3 into 10 to the power minus 3. ये देखो मिली एम्पियर है minus G. And when you simplify it, you get this, see 3 6 18 और ये 10 to the power minus 3 ऊपर जाएगा तो दे देगा आपको 6000 minus 12 this much 5988 ohm. Very high resistance. And resistance of voltmeter. Now resistance of voltmeter is G plus R. So G is 12 and R अभी हमने निकाला और दोनों का सम can see 6000 ohm. And as I told you, voltmeter has very high resistance. So it's a very simple problem, but ये problem board में आते हैं. Another unsolved problem from your NCERT book only. A galvanometer has resistance of 15 ohm and the meter shows full deflection for 4 milliampere. How will you convert the meter to an emitter of range 0 to 6 ampere? So आपको range I की value दी है 6. Ig is given to be 4 milliampere and G is given to be 15 ohm. And this shunt resistance is connected in parallel with the galvanometer. So putting all the values here, see Ig is 4 milliampere and milli is 10 to the power minus 3 upon I is 6 minus 4 into 10 to the power minus 3 into G. Now here I have made some approximation. If you look at this term, this will be 0.004. 0.004. See? Now this is too small as compared to 6. 6 में से इसको माइनस करोगे तो बहुत ही छोटा है. So we take it nearly equal to 6 only. So this is nearly equal to 4 into 10 to the power minus 3 upon 6 and into 15. Multiply, simplify, you get 0.01 ohm. Very, very small. And I have already told you that shunt is a very small resistance. So 0.01 ohm. And now resistance of the emitter. Now resistance of emitter is Gs upon G plus S. And put the values. So here again, what do you get? 15 into S is 0.01 upon 15 plus 0.01. So see 15 plus 0.01. This is negligible as compared to this one. So this is nearly equal to 0.01 ओम। सो पूरे एमीटर का रेसिस्टेंस जो है इतना कम आया, और आपको बताया था कि आइडियल एमीटर का रेसिस्टेंस 0 होता है। सो लेट अस मूव ऑन टू नेक्स्ट अनसॉल्व्ड प्रॉब्लम। Look at it. A square coil of side 10 centimeter consisting of 20 turns carries a current of 12 ampere. The coil is suspended vertically and the normal to the plane of the coil makes an angle of 30 degree with the direction of uniform horizontal magnetic field of magnitude 0.80 Tesla. What is the magnitude of torque experienced by the coil? A very simple problem. Torque is equal to NIAB sin phi. You have just done. And here the total number of turns is given to be 20. Current 12 ampere. Area vector is, see, square coil hai and side is 10 centimeter. So area is 0.1 into 0.1 square meter. SI unit लेनी है आपको. And this is equal, and the angle between the normal to the plane of the coil and the direction of magnetic field is 30 degree. So phi is given to be 30 degree. Sometimes the angle between plane and the magnetic field is given. Supposing अगर ये नॉर्मल ना कह के केवल प्लेन कहा होता तो फाई की वैल्यू 60 डिग्री हो जाती. सो यू मस्ट पे अटेंशन टू दिस पार्ट विच क्रिएट्स कंफ्यूजन. ओके, सो पुटिंग ऑल द वैल्यूज हियर, टॉर्क इज इक्वल टू 20 into 12 into this one, sin 30 is 1/2 and you get 1.2 Newton meter. Question में पूछा नहीं है but often it is asked. Net force on the loop is 0. And another NCERT problem only. Look at it. Two moving coil meters M1 and M2 have following particulars. R1 10 ohm, N1 30, A1 3.6 into 10 to the power minus 3 square meter, B1 0.25 Tesla. R2 14 ohm, N2 42, area A2 1.8 into 10 to the power minus 3, B2 is 0.50 Tesla. The spring constants are identical for the two meters. Now, determine the ratio of current sensitivity and voltage sensitivity of M2 and M1. इनकी current sensitivity और voltage sensitivity का ratio निकालना है. And the relation for current sensitivity is NAB upon K. So, first we will find out ratio of current sensitivity. K is constant according to the question. So, current sensitivity of M2 पहले है, upon current sensitivity of M1 will be equal to, see, K is constant, so neglected. So, S2 के सामने सारे S2 वाले, N2 A2 B2, S1 के सामने S1 वाले, N1 A1 B1, direct relationship. Put all the values from this relation and you get 7 upon 6. Now, see, the voltage sensitivity is NAB upon KR, and this NAB upon K is current sensitivity. So, I can put current sensitivity upon R, right? And from here, you can see that voltage sensitivity and resistance are inversely related, and voltage sensitivity and current sensitivity are directly related. So, when you take the ratio of second coil, see, voltage sensitivity of second coil upon voltage sensitivity of first coil is equal to, यहाँ पर डायरेक्ट इसका डायरेक्ट रिलेशन है, सो आई कैन राइट S2 अपॉन S1, और R के साथ इन्वर्स रिलेशन है, सो R1 अपॉन R2. S2 upon S1, this is 7 upon 6, we have just calculated, and R1 upon R2, putting the values, simplifying, you get 5 upon 6. So students, you have to learn to simplify your work. आपको काम छोटे से छोटा करना है. This again is a very interesting problem, an unsolved NCERT problem. A uniform magnetic field of 3000 Gauss is established along positive Z direction. A rectangular loop of side 10 cm and 5 cm carries a current of 12 ampere. What is the torque on the loop in different cases as shown in this figure, and what is the force on each case, and which case corresponds to stable equilibrium? So yeah, look at it. Please pay attention to the diagrams now. Now according to question, magnetic field is set up along z-axis. Here we are showing z-axis. This is x-axis, this is y-axis, and this loop is given. And the sense of current is given in each case. So you see sense of current here shown in each case, and different orientations of this loop. See here it is placed in YZ plane, here it is placed in YZ plane, here it is placed in XY plane, XZ plane, and this is midway between them. This is in XY plane, this is also in XY plane. And sense of current, you cannot ignore the sense of current. Like here it is anti-clockwise, anti-clockwise, here it is clockwise, this is anti-clockwise, anti-clockwise, clockwise. So in this way, you have to find out torque acting on this coil in each case, right? So we'll take the cases one by one. So to begin with this one, here the B is along Z, and torque is equal to M cross B, right? So we need to find out M also. Current is known to us, the sides are known, we can find out area vector. And if you look at this one, the current is anti-clockwise. And if you see, if you use the fingers of your right hand to curl along this sense of current, then extended thumb will give you the direction of magnetic field and it will give you the direction of the magnetic moment. आप अपने राइट हैंड की फिंगर्स को इस करंट की सेंस में टर्न करें, कर्ल करें, तो आप जो आपको थंब है वो मैग्नेटिक मोमेंट m की डायरेक्शन देगा, and according to this it will be along the direction of x-axis, positive x-axis. Okay, so let us look at the solution now. The magnetic field is 3000 G Gauss, and Gauss is 10 raised to the power minus 4 Tesla. 1 Gauss is equal to 10 raised to the power minus 4 Tesla. So if I put this value here, you will get 0.3 Tesla. Okay. The area vector is 10 centimeter length into breadth, or you have to convert it to a square meter. So multiply by 10 raised to the power minus 4 square meter. The current is 12 ampere. Now magnetic dipole moment is IA, and I is 12, area is, simplifying it, you get 5 into 10 to the power minus 3 and this much. This is the magnitude of the dipole moment, 6 into 10 to the power minus 2 ampere meter square. Now magnetic field is 0.3 K cap. See, the field is along z-axis, positive z-axis, and the unit vector along plus z-axis is K cap, Tesla. Now magnetic dipole moment in first case is NIA, N की value 1 है, its magnitude this much, or this dipole moment is along x-axis. So the area vector here, the unit vector here is I cap, right? Ampere meter square. Now this should be very very clear to you. और आपको मैग्नेटिक मोमेंट की डायरेक्शन निकालना आना चाहिए. Okay? Now in this case, the angle between M and B is 90 degree. So the torque is equal to M cross B. You know this formula, or MB sin phi, and you can put the values. M की वैल्यू डाल दिए, B की वैल्यू डाल दी, and sin 90 is 1. You get 1.8 into 10 to the power minus 2 Newton meter. This is the magnitude of the torque. Now I have to find out its direction also. So torque is equal to, see, okay, when you're doing this, M का यूनिट वेक्टर है I cap क्रॉस B का यूनिट है K cap, एंड क्लास 11th का अगर आप याद करें तो I cap क्रॉस K cap is minus J cap. This is equal to minus J cap, class 11th vector product, right? So that means the torque is given by minus the magnitude 1.8 into 10 to the power minus 2 J cap Newton meter, और minus J cap है तो it is along minus y axis. So these directions should be very clear to you. And net force on the loop is 0. Now let us move on to part B. Okay, so let's go back to the diagram here. And yeah, see, the magnetic field is same along z-axis, and ये जो आपका लूप था अब इसकी ओरिएंटेशन चेंज कर दी है, but if you see the orientation, the sense of current is anti-clockwise here, and here also it is anti-clockwise only, और एरिया उसका वही है, एरिया नहीं चेंज हो रहा है. So direction of magnetic field will be along this, direction of area vector will be along x-axis, and direction of magnetic moment will also be along x-axis only. So that means it is exactly same situation. यहाँ भी direction of magnetic moment इधर ही थी. So this situation and this situation are same only. So you will get the same result. No change. Part B. M and B have not changed, so the torque is same as this one along minus y axis, and net force experienced by the loop will be 0. So second case में result में कोई change नहीं आया. Now let's see what we get in the third case, part C. Now part C is, let us look at this diagram here. Great. See, magnetic field is along z-axis, और यहाँ पर this current is moving like this one, and अगर अपनी उंगलियों को आप कर्ल करेंगे करंट के साथ में तो आपका थंब जाएगा पीछे की तरफ, राइट, along minus y axis. ठीक है? So your magnetic moment is along this direction, right? And if that is the case, then we will find out the product now. And y-axis है तो we have to use J, right? Because now this coil is in plane of xz. So let us look at this, how we treat it. So the magnetic moment is NIA, and it is minus 6 into 10 to the power minus 2 J ampere meter square. See, the direction of this M is along minus y axis, and minus y axis is minus J cap. Now torque is equal to m cross b. प्रोडक्ट तो देखो अभी भी वही रहेगा क्योंकि एंगल बिटवीन m and b इज 90 डिग्री एंड डायरेक्शन इज, अब यहाँ पर हमें क्या चाहिए, माइनस j cap. So what we are getting, product of minus j cap cross b is along k cap and j cross k is I cap. So you get minus I cap, right? So now you get minus I cap here and the magnitude is same. So it is along minus x axis and net force experienced by the loop is again 0. Okay. Now let us look at the next part here. See, very interesting problem. Different orientations, same loop. So here magnitude, the magnetic field is along z-axis only, and now this coil is turned here. The angle between this coil and y-axis is here 30 degree with the plane. And now if you want to find out the area vector, see, area vector will be like this one. So it is 30 degree here plus 90 degree here, 120 degree from here. I'll get 120 degree from here. So it will go till this point, right? And angle between B and M is still 90 degree. You can see that angle between, because this M will be in xy plane only. So this B and M are perpendicular to each other, but the M is, in this case it was along x-axis, in this case it was along this axis, in this case M was along y-axis, but here the direction is changed by 30 plus 90 degree. So now look at the relation here. The angle between M and B is 90 degree without any doubt. M makes angle of 30 plus 90 with y-axis 120 degree. So torque, same magnitude, Newton meter at 120 degree with this x-axis. Okay, and now the problem is, here I cannot show you any I cap or j cap or whatever. So the net force acting on the loop will be 0. And the next case, again for this I have to go back to the diagram here. Now in this case, magnetic field along z-axis here, and the loop lies in xy plane. So here if you curl your fingers along the sense of current, you get it in upward direction. See, so magnetic moment is in upward direction and magnetic field is also along the same direction. So this B and M are parallel. So the torque acting on them is 0, but this is a case of stable equilibrium. When M and B are parallel, it is case of stable equilibrium. And let us look at the second case also. Here the sense of current is changed, you see. So now the magnetic moment will be downwards and magnetic field upward already hai. So B and M are in opposite direction. So this is case of unstable equilibrium and this is case of stable equilibrium. When M and B are parallel, it is stable equilibrium, and when M and B are anti-parallel, it is unstable equilibrium. So see part E. M and B are parallel, so torque is M cross B is equal to 0. You know, parallel vectors का cross product 0 vector होता है. Stable equilibrium, net force is 0. Here M and B are anti-parallel, और anti-parallel भी है तो product will be 0 vector. Unstable equilibrium, Now net force acting on the loop is 0. So this was a really very interesting problem. And with this I come to the end of this video. Thank you very much for watching, and I hope that it is beneficial to